All right, now I want to give you an idea of potential energy and work. Okay, so consider this. Consider a mass. Let's call that mass M. And this mass has some forces acting on it. So obviously, because it's on Earth, it's in Earth's gravitational field. So it has the force of gravity that pulls down on it. Let's call Fg. Let's say I have placed my hand underneath this mass and I want to raise it up. Okay, so then if I place my hand underneath this mass, therefore I'm exerting a normal force, and that force is directed upwards. All right, let's call that Fn, or let's call that F me, just to be very clear that it is my force that I'm applying. So let's call that F me. All right, so now then I can say, okay, I move it from one point in space. I give that point, let's call that y equals 0, and I move it up to some certain distance. That's, let's call it y equals h. All right, so what is the work that I do? Because I'm applying a force, I'm moving something a certain distance, then I'm doing some work. So the work is defined as the integral of the force dot the small displacement each time I'm making a movement. So F dot dx. The F is the force that I'm exerting, F sub me. Expanding out the dot product by definition tells me that it is F, the magnitude of F sub me, times the magnitude of the displacement vector, times cosine of the angle between F and dx. So what is the direction that I'm moving in? Well, I'm obviously moving upwards. So this is the direction of my displacement. So this is parallel to my force. So therefore, the angle of cosine is 0, and cosine of 0 is plus 1. So every time that I'm doing work, this is the work done by me, to raise something up a certain height, I'm doing positive work. Now let's say I move it up slowly. That is, I have no acceleration. Okay, so now I'm moving it up in a way that is, I'm moving it at constant speed. At constant speed means that since there is no acceleration, no unbalanced force, so the F sub me is exactly balanced out by Fg. And you know what Fg is. It's nothing but mass times the gravity, right? Mass times 9.8 for Earth. Then Fg is equal to Fme, so therefore my work becomes, the work done by me to move this object a little bit distance upwards, is mg, which is a constant for each mass, and this acceleration is a constant, integral of dx from, I should have been clear, I probably should have written it as dy, but it doesn't matter what you call it at the end of the day. Let's call it dy, all right? So dy, I'm raising it up from a reference point, from y equals 0 to some y equals h. Then this integral is very simple. It gives me the work that I do. The work done by me is mgh. You recognize this formula very well. This is the potential energy, or rather the change in the potential energy, okay, of gravity, U sub g. Why change? Because potential energy, you're always having this reference point where the potential energy is 0. So always there is y equals 0, with which you're comparing whatever this h or height is. So then you do positive work, I do positive work to raise this object upwards. I give it a more potential energy. So my positive work equals a positive change in the potential energy of the mass, right? Conversely then, I can now focus on the work done by gravity. The work done by gravity then is nothing but Fg is the integral of force of gravity dot dy. Now I'm very careful. This you can expand out. This is mg, right? Integral of dy, but the angle now, Fg is downward, displacement is upward. I'm still moving it up in the same motion. I'm moving it up, but force of gravity is acting downwards. So cosine of the angle becomes cosine of 180. Now cosine of 180 is minus 1. So the work done by gravity for the same motion from 0 to some height h is negative mgh. h. So therefore, gravity does negative work when you do, or when I do, positive work. So how do I relate it to gravitational field? Well, gravitational field on Earth, everywhere, I can approximate it as being uniformly downward, right? Everywhere. And if I place some mass here and I'm raising it up, I'm moving it against the field. This is the field of gravity. And I'm moving it up by exerting a certain force. I'm moving it upwards against the field. So when I'm doing work against the field, I'm doing positive work. Gravity is doing negative work. So when gravity is doing negative work, then the object's potential energy is increasing, because see, you're going up from y equals 0 to some y equals h. Your potential energy of the mass is increasing if you're moving against the field. The very same idea applies to electrostatic cases. So I won't go into the derivation of everything. I would just give you this concept. You have a positive charge placed near another positive charge. One is, let's say, Q1, the other is, let's say, Q2. They're separated by some distance. Let's call that R. Then I know how to define work done. So how did I place Q2 here? Well, Q2 was originally with me somewhere at infinity, right? This is plus Q2. I brought it in from infinity to somewhere here, and I brought it in by exerting a force this way. So this is F sub me, to move it also this way, right? Therefore, the work I do again is integral of the force that I exert dx cosine of 0, which is again positive work. The work done by the field, remember, if I bring it in near Q1, which is another positive charge, the force, the electrostatic force, would be to the right. This is F sub E. So F sub E is rightward, but I'm moving this in leftward. So the angle between FE and the displacement dx is 180 degree. So then this is the work done by the electric field is negative the work done by me. All right. So therefore, that is the idea that easily translates into electrostatic cases from gravitational. And you know very well the formula to calculate potential energy of 2-point charges. The potential energy U sub E is 1 over 4 pi epsilon 0, or just K, times Q1 Q2 by R. At infinity then, when R is at infinity, very far away, the potential energy is 0. Okay, so because then Q1 doesn't know of the existence of Q2, because Q2 is so far away that there is no potential energy of this charge configuration. All right, so so the potential energy is always set to 0 at infinity. That's the fixed reference point. All right, so when I bring in this positive Q2 from infinity to this some point R near Q1, I'm doing positive work. So this is basically the work that I do. All right, and of course then gravity does, or not, sorry, not gravity, then the electric field does negative work. All right, so the electric field, the work done by the electric field is negative. I'm very messy here. Let's be a little bit more careful. Is negative. All right, now let me give you a context. Let me give you some context to this. So let's say now we have electric fields. So let's say we have an electric field going this way. This is the electric field. This is electric field. And now you ask me to do something for you. You hand me a positive charge. Let's call that this little positive sphere. You hand it to me and you say, I have a job for you. You make it move against the field. So, okay, your wish is my command. So I would basically exert a force, apply a force in the opposite direction to the field and try and move it in that direction, right? So I'm trying to create the displacement in this direction. So what am I trying to do? I'm trying to move against the field. Similar to your gravity case, whenever you moved against the field, gravity is always downward, you're trying to move upward, that increased the potential energy by an amount h of the object. Similarly, if you are trying to move a positive charge against the field, then you're increasing the potential energy of the positive charge. So the potential energy, the electrostatic potential energy of the positive charge goes up because you do positive work. So work done by me, or I do positive work, is also positive, but the field, work done by the electric field, is negative. Okay, now again let me give you another context. Let's say again we have electric field, the same electric field we had before, that's directed to the right as such. All right, now you have a different job for me. Now you say, I have another job for you, but this may be a little bit more difficult. I want to bring in, you hand me a negative charge and you say make it move in the direction of the field, right? I say, okay, well, previously I had a charge that I wanted to move against the field, so I did some work, I wanted to go against something. But here I have this negative charge. Am I going against something? That's not quite easy to think about. But let me give you some other hints. Well, imagine, what is the direction of the electric field really? Electric field is always away from or out of a positive charge and going towards or into a negative charge. So whenever you have a direction of the electric field, then you can always imagine at the start of the electric field there is some positive charge in space. At the end of the electric field there is some negative charge in space. So therefore, when you handed me a negative charge, this green negative charge, then I had to do something that the negative charge doesn't want to do. I want to push it close to another negative charge, right? So, and here is an imaginary negative charge because there is where the electric field is going towards. So going towards a negative, I am also trying to push this negative charge towards this negative charge. It doesn't like me very much. It doesn't like that negative charge very much. So I'm opposing the natural tendency of the field, or of the negative charge, which always wants to go against the field. So negative charge, let me write that down for you. Negative charge always wants to go against the field. Okay, so when I'm trying to move it with the field, I have to put in some effort. All right, so now I'm pushing the force. I'm basically doing, like I want you to pause here and think, what work am I doing? Am I doing positive work or am I doing negative work? All right, now that you have thought about it, hopefully I've answered the question before me. The work that I'm doing, I'm applying a force to the right, I'm trying to move it to the right, so of course I'm doing positive work. So work done by me is positive, which automatically means the work done by the field is negative. So when the work done by the field is negative, basically you're going against the wishes of the field. That increases the potential energy. So the electrostatic potential energy of the negative charge goes up. Okay, so think about this a little bit and then play around with the electric fields. Maybe reverse the direction of the electric field. Maybe think about, I will give you a homework myself now. Maybe think about if I hand you a positive charge and ask you to move it in the direction of the field, what happens? Do you increase the potential energy of the system of the positive charge, or do you decrease the potential energy of the positive charge? Think about it and get back to me. Thank you.